Hello. Today, I will be talking about partial fraction decomposition and how it can be used to integrate rational functions, that is, a polynomial over a polynomial. And this works because any polynomial can be factored as a product of linear factors and quadratic factors. Now, to integrate a rational function, we will express it as a sum of partial fractions using partial fraction decomposition. Typically, when summing fractions, we find a common denominator in order to sum them. Partial fraction decomposition essentially reverses this product. We start with a composed function. We decompose it into a sum of partial fractions. So let's take a look at this integral. In order to use partial fraction decomposition, the denominator will have to be factored completely. So in this case, we'll have as our denominator x plus 5 and x minus 2. From here, I'm going to ignore the integral for the time being and just evaluate the fraction. And what we're going to do is decompose this fraction here by splitting up our distinct linear factors, x plus 5 and x minus 2. They're going to become their own fractions, the denominator of distinct fractions, each with a variable as their numerator. And then we'll be solving for the variables. In order to do that, we'll multiply by our common denominator. Once doing so, we are left with a times x minus 2 plus b times x plus 5. Now, in order to solve, let's plug in x values that will eliminate one of our variables, allowing us to solve for the other. Let's start by solving for a. So we'll plug in negative 5 for x. So when x equals negative 5, we'll have negative 5 minus 9. Negative 14 equal to negative 5 minus 2, negative 7a. So we start a little tally. We have a equal to 2. Now to solve for b, let's eliminate a by setting x equal to 2. When x equals 2, we've got negative 7 equal to 7b, which looks like b will equal negative 1. Next, we'll plug in these values that we found for our variables. I'll reconstruct the integral as well. So our original integral is now equal to, I'm going to leave these as separate integrals. A is equal to 2, so we have 2 over x plus 5 plus the integral, actually, minus the integral of 1 over x minus 2. Now that's a lot easier to solve than our original. In fact, let's do that. So this will have 2 times ln of x plus 5 minus natural log of x minus 2 plus c. That'll be our answer. Next, we will look at different cases where we will use partial fraction decomposition. This first one was in the case of distinct linear factors, none of which are repeated. And that's just one of 4. So let's look at the next one. Okay, looking at our next example, we have the indefinite integral of x plus 3 over x cubed plus 2x squared. We're going to start again by factoring the denominator. Pull out an x squared, we'll be left with x plus 2. Now what's different here? So we have x squared, this repeated factor of x times x. Since that is repeated, we'll have to change our process just a bit. So looking at the fraction, we'll start assigning our variables. Beginning with a, we'll put that over just the first occurrence of x. And b will be over the second occurrence of x, or x squared. Both x's are accounted for, so we'll finish with c over x plus 2. From here, it looks pretty similar to the last one. So we will start solving for our variables by multiplying through by our common denominator, leaving x plus 3 equals a times x plus 2 plus b times x plus 2 plus c times x squared. I'm going to multiply this a part out. X squared plus 2x. The rest I will leave. Okay. Now, let's start eliminating some variables by choosing x values. Let's start with x equals 0, huh? So if x equals 0, 0 plus 3. 3 equals 0. 2b. That's it. So, looks like b will equal 3 halves. I'll set these over here. So b equals 3 halves. Great. Next, let's choose x equals negative 2. And we'll eliminate b. So negative 2 squared, 4, plus negative 4. 0. 0. C, though, will equal 4. 4c will equal 1. So c will equal 1/4. For a, we are going to have to use b and c. So let's look at x here. So you can imagine x having this coefficient of 1, right? Now, let's look for x's attached to our variables, basically. So we're going to have a bx here, right? And a 2ax here. And again, on that side, we have 1. So 1 times x on the left side is equal to, what did we say? We have 2a plus bx. Now, we see that 2a plus b must equal 1. We have b equals 3 halves. So 2a plus 3 halves equals 1. Which means a equals negative 1/4. So now that we have found the value of our variables, we'll reconstruct the integral. So the original indefinite integral is equal to a over x. We have negative 1/4. Now I'm going to leave this out of the integral. It's a constant. So we'll just be left with 1 over x dx. I'll do the same with b. b equals 3/2 times the integral of 1 over x squared. Lastly, c equals 1/4 times the integral of 1 over x plus 2 dx. Great, easy enough to solve, no? I'm rearranging a bit just to lead with a positive.
Minus 3 over 2x.
Plus c. Okay, let's look at our third example. We have the indefinite integral of x squared minus 1 over x cubed plus x. After factoring the denominator, we're left with x squared minus 1 over x times x squared plus 1. And you'll see we're left with this irreducible quadratic function in the denominator. So, when we evaluate the fraction, a over x, easy enough for that single factor of x. But for this quadratic, the variables we'll use are bx plus c over x squared plus 1, so that numerator has a factor of x with a degree 1 less than our denominator. And that's the case with any quadratic function left in our denominator. From here, we'll evaluate it similarly. We'll multiply through by our common denominator. So x squared minus 1 equals a times x squared plus 1 plus bx plus c times x. And let's start choosing x values to solve for these variables. Let's start with x equals 0. Both of these will get knocked out. 0 minus 1, negative 1, equals 0 plus 1 times a, so equals a. a equals negative 1. Great. Now let's choose. Now let's look at the coefficient of x squared. You can imagine a 1 here. On this side we have attached to x squared we have an a. Here we have bx squared if I multiplied that through. So we have 1 x squared on the left. On the right we have a plus b x squared. We know that a equals negative 1. So it looks like b is going to equal 2. Great, and for c, looks like c is the only variable attached to a single x. And on this side, we have no x's. So to visualize this, we have 0 times x equal to c times x. As we can see, c equals 0. Now that we have our values for the variables, we can recompile and solve the original integral. So our original integral is now equal to the integral of a over x, a equals -1, plus the integral of bx plus c, where b equals 2 and c equals 0. And that's over x squared plus 1. So after u sub, we would have, and again I'm going to flip the order of these so the positive is first. That's all I'm doing. After u sub, we'll have ln of x squared plus 1 minus ln of x plus c. And why not? Let's use quotient rule. There it is. Okay, I've set up a fourth example here. Now that we've solved 3 examples of partial fraction decomposition, something like this should be no problem, right? Let's give it a shot. Now the first factor in the denominator is a lone single x. We know what to do with that. But now we've got a quadratic squared. We know what to do with repeated linear factors. We know what to do with quadratic factors. But with quadratic factors that are repeated, thankfully, the process is basically the same for repeated linear. We'll start with the first occurrence of x squared plus 1 bx plus c over x squared plus 1. And then we just need to repeat that quadratic factor and add some variables up top, dx plus e over x squared plus 1 quantity squared. That's that. I'm not going to go through the process of solving for these. We've done it. But I'll tell you what they equal. A equals, let's see, 2, B equals -1, C equals 1, D equals 3, E equals -2. Right? Yeah. So now we can evaluate our original integral with our partial fractions. Let's see. We've got a equals 2. So e equals 2 times the integral of 1 over x dx. B is -1. So we'll have minus the integral of x plus c equals 1. So x plus 1 over x squared plus 1 plus the integral of dx plus e, where d equals 3 and e equals -2. And that's over x squared plus 1 squared dx. And we're left with
2 times ln x minus ln x squared plus 1 over 2 minus x over x squared plus 1 minus 3 over 2 x squared plus 1 plus c.
And there you have it. So, lastly, I would like to walk you through a method which can expedite the process of solving for variables in partial fraction decomposition. It's called the cover-up method. It can be used when your denominator consists of linear factors. They can be repeating. I'll just walk you through it. We have a fraction. Our original fraction is 1 over x plus 1 times the quantity of x plus 2 squared. I've set up the partial fraction decomposition here, but instead of expanding everything out by multiplying by the common denominator and all that, we'll start looking at a over x plus 1, and we'll consider how we can cause this denominator to equal 0. Which x value will make this 0? In this case, -1. Let's remember that. So, x equals -1. And now we're going to cover that up, that x plus 1, in the denominator of our original, and plug -1 in for x in the remaining factor. So -1 plus 2 is 1 squared is 1. 1 over 1 gives us our a value equals 1. Now let's do the same for c. Now we can't do it for b, because in order for this cover-up method to work, your denominator in your partial fraction has to be exactly represented in the original. Now here we don't have x plus 2 in the original, but we do have x plus 2 squared, hence why we can do it with c and not b. So with c, how can we make this denominator 0? Well, x equals -2 would do that. So x equals -2. And now we'll cover this one up and plug in that -2 to the remaining factor. -2 plus 1 is -1. So 1 over -1 gives us our c value of -1. We've got b left to solve for. We can't do the cover-up. Thankfully, that doesn't mean we have to expand everything out like the previous examples. Thankfully, we can, since we've solved for other variables, we're only left with one unknown. We can just plug in any old x value and solve for b. So let's choose x equals 0 and evaluate through. So we have 1
over 0 plus 1 is 1 times 0 plus 2 squared, 4. So 1 over 4. A equals 1, and then over 0 plus 1 is 1 plus.
We don't know b over
0 plus 2 plus c, well, c is -1, so minus 1 over 0 plus 2 squared, 4.
Now I'm going to clean this up and put everything over 4. And let's see, 4 minus 1 over 4 on this side. So 1/4 minus 3/4, -2/4 equals 2b over 4. So it looks like b equals -1. And that's the cover-up method. Now, I would just like to leave with a summary of the processes we've learned, a more general form of partial fraction decomposition. Now, if we have distinct linear factors in our denominator, here's the general form of our partial fraction, just a constant over each distinct linear factor. If we have repeating linear factors, we need a distinct variable over each occurrence of the linear factor. With quadratic factors in the denominator, we just need to add that x variable to our numerator. And now if those repeat, the quadratic repeats, again, we need a distinct numerator for each occurrence of the quadratic factor. Well, thanks for watching. I hope it was helpful.